Hi folks, this is Christian. I'm a software engineer and today I want to show you a little bit about my NVIDIA DGX Spark. I want to share some basics, tooling, ecosystems, some challenges I had, some personal experiences, and some benchmarks. So this is a slide deck I presented 6 months ago in Bend, Oregon for a developer audience, and it's all about what Sparky is and what you can learn. Last summer, I had the problem that I really wanted to learn more about AI in general, and especially the infrastructure behind the API endpoint. Till then, I had done some agent projects, vibe coding, MCP tooling, some automation around it. So I was thinking about like laptops are too slow, big workstations are very expensive. I also didn't really know what I needed. And cloud setup is always a little bit of a struggle, and costs are not clear. And then you have like and not direct access to all the optimizations. So it's pre-packaged. So the DGX Spark sits right in the middle. So what I really wanted to get is a GPU computer sitting on my desk and being able to do all the things like installing all the latest technologies, models, inference runtimes, all those things. I remember the motivation for Sparky was born in the summertime in Seattle, sitting in the garden with a friend. At that time, I was going to 2 AI conferences in San Francisco, one for AI infrastructure and one for AI engineering. So I really wanted to learn a lot of things. I knew that NVIDIA is leading the market. I wanted to learn rack systems, graph databases, all about inference and all the different models and how to train them. And knowledge graphs. I followed it for years, due to a conference in New York from the Cornell College. And coming from a hyperscale compute distributed runtime, I really was interested in what does it mean like to do distributed inference in the data center. So LLMD is something I wanted to learn. And of course, I wanted to look into multi-agent frameworks. So what was the best thing I could do at that point? I knew like I want to have access to the NVIDIA optimizations, to all the systems. They have their local development story with DGX Spark, and having the hardware with the specialized GPUs is the closest thing you can get to real infrastructure, access to leading tools. We need to talk about the box design and the phenomenal GB10, the GPU in the DGX Spark, based on the NVIDIA Blackwell architecture. Comes with 6,000 CUDA cores, responsible for arithmetic and logic operations. It comes with 192 tensor cores, responsible for matrix calculations. It supports sparse FP4 operations, which basically means it can skip all the 0 values. And FP4 is a floating point format, which is used to compress model weights. Model weights needs to be loaded fully in memory to actually use the model. So compressing the model weights is half the memory size in comparison to FP8, for example. Taking the example of NVFP4, NVIDIA's own FP4 format, they compress the model weights in small blocks with scaling factors to improve accuracy. So that is a different approach than the standard FP4. Then the accuracy is pretty much the same. There's less than 1% quality loss with FP4. So that is huge. What else? The GB10 cannot natively use FP4 for gem calculations like the B200. So for the GB10, it is converted to BF16 for this special task. That's a little bit different, but important. So it's also a little bit different architecture than the B200, the data center version of the Blackwell architecture. You need special CUDA kernel versions to optimize for this GPU. Most of the things are very similar. The GPU supports up to 3 gigahertz, and that means we have like around 3 billion cycles per second, or 0.33 nanoseconds per cycle. If you think about that, the GPU can support 1 petaflop of FP4 operations per second, that is about over 333 FP4 operations per clock cycle. So, but why is that important? Depending on the model architecture and the hardware architecture, you need different kernel optimizations. So you want to make sure that all the cores are fully leveraged all the time. So basically, you use kernels to program the work. So you send it to the GPU, the so-called warp scheduler, distributing the work to the SMs, the streaming multiprocessors. Multiprocessors group cores to distribute the work. So all those units, like the SM, have shared memories. The group of SMs have shared memories. Core has a register, which read time is 1 cycle. The shared memory for SM is 20 cycles. For the shared memory for all SMs is 100 cycles. And if the GPU wants to read data from the memory, it's 200 or more cycles. So you really want to make sure that the work is packaged in the right way to the right time. So that is why we have so many kernel developers out there. So another thing is that the GB10 has a 20-core ARM processor. And most unique about this box is actually the 128 GB LPDDR5 unified system memory. That means that the CPU and the GPU can access the same data in the same memory. If you have a normal workstation, you have memory and you have VRAM on the GPU. And if you need data in the GPU, you need to copy it from the RAM to the VRAM. That is not needed for the GB10. The LPDDR5 has 273 gigabyte per second bandwidth, which is a little bit limiting when it comes to decode. So actually generating the next probability of the next token. It's still pretty fast, and with batching and the right configuration and more CUDA optimizations to come, you have a pretty decent performance. So what else? 4 terabyte of storage, network adapter, and you have a data center grade network component in the box, which is the Connect X7 SmartNIC, which basically allows you to connect multiple DGX Sparks, and you get 25 gigabyte per second bandwidth, like for transferring KV cache, pretty important. Wi-Fi 7, pretty smooth. You can setup is pretty easy. You just connect to the hotspot and just place it somewhere in the house and just go with the laptop, or you just connect a monitor and mouse and keyboard to work as a desktop PC. Okay, let's talk about some numbers. I picked 3 DGX systems to compare the AI performance and some numbers from the hardware perspective. I'm sure you can go much deeper, but I thought maybe that might be helpful to get an idea where we are with this DGX Spark. So the DGX Spark is the middle. I picked the DGX one from the first one from 2016 on the left. It had 8 Pascal 100 GPUs, over 28,000 CUDA cores, 0 tensor cores because they were not invented at that time, and 128 gigabyte of HBM2 memory, which has a bandwidth of 900 gigabyte per second. That's important. And the AI peak performance is 170 teraflops on FP16. 9 years later, the DGX Spark has 1 Grace Blackwell GPU with over 6,000 CUDA cores, 192 tensor cores, 128 gigabyte of RAM unified DDR5, which has only 273 gigabyte per second. And the AI peak performance is 1 pflop on FP4. So almost double than for the DGX1 in 2016. So The 2x peak performance comes from tensor cores and from the machine running on 3 gigahertz instead of 1.5 for the DGX1, and a lot of software improvements and chip improvements. And it's a fair price, I think. I know that many people say it's expensive, but there's nothing comparable in the market. If you take consumer graphic cards, you don't reach the same power peak performance, because you need not only decode, you also need prefill, and you need the software stack and the optimizations, and that is key. Even with an Apple Studio, you might reach the similar decode performance, but not prefill. And when you use decode and batching, you even get more with DGX Spark. But it goes a lot into details and a lot of configuration, and most people don't want it. But let's continue with the comparison. So the data center DGX B200, so Blackwell 200, has 8 GPUs, over 186,000 CUDA cores, over 4,600 tensor cores, and 1,440 gigabyte of RAM, HBM3E, which has a bandwidth of 8 terabyte per second. That's massive. And the AI peak performance for the DGX B200 is 144 petaflops. So there is a quadrillion floating point operations per second, or 15 zeros. Okay, let's look at the software stack and some resources for training purposes and better understanding of the system. The operation system is a customized Ubuntu version, behaves as normal, is not locked down. It just comes prepackaged with some libraries, drivers, and tools. Most people would use the system via terminal. The tools made it really easy for me to understand the system. And there's NVIDIA Sync, which is a quick connect tool, a system tray tool. I show you that in a second to just get some shortcuts. To integrations, there's a dashboard. It's good for quick check, and it's good for update management if you don't want to do it via terminal. AI Workbench, cool tool to manage projects or samples and deploy to different systems like local, Spark, GPU Cloud. Jupyter Lab, super nice for like experimentation. You have all these code cells which you can execute, and then you have the history of the results, and you can mix it up with some explanations. So if you want to write a guide for somebody to follow through, like some experiment you had, this is the way to go. Then there's NIM. It's an Inference microservice packaged Docker container, where you basically just use Docker run, and then you get an endpoint with the LLM of your choice. Then there's Brave, which is a massive amount of blueprints, so-called launchables. They're really amazing repositories on GitHub, which explain industry scenarios, like really applications. To go deeper, it's perfect, and you can also just do a one-click deployment into a GPU cloud. So the NGC is a GPU cloud. I think it's just a facade to really deploy to cloud provider or neo clouds, but it's also a container registry where you get all kinds of containers for the DGX Spark. I think most important is actually a website with a lot of playbooks where you'll learn how to set up the DGX Spark and how to configure special scenarios, application scenarios. We will take a look. And then there's a forum, a developer forum, which is where people are super active, super nice communities. People are eager to test out the latest optimization, latest updates from Inference runtimes. They present proudly their DGX Spark stacks. Like people have like 4 or 8 machines or even more. Yeah, and there also are some good community projects. All right, let's look at some tools. So first of all, let's look at the NVIDIA Sync tool. You configure your Spark systems, and then you just connect to it, and then you get some shortcuts for tools tools with direct integration into DGX Spark and some custom shortcuts where you can configure bash scripts or just an URL for something which is running on your DGX Spark. So let's look at the DGX dashboard. It's, oh, okay, let me move that over here. It's basically a simple web application. It's not customizable. You get 2 metrics, system memory and GPU utilization. Usually you would probably use some tools like BTOP or Grafana dashboards, but I guess that's a quick test. It's good. You have update management here. You can do that via terminal too. And you have Jupyter Lab, which you can just start in the browser. So pretty handy. You basically can just look through your experiments and just execute cells, and then you can go through it, and it's pretty good for learning. Back to the NVIDIA Sync, the AI Workbench tool. I said it's good for managing projects, good for managing different remote machines. So you can deploy that project on your local machine or on your Spark or in the GPU cloud or any other machine with SSH connection and the client. So let's connect to a project I have loaded. So I loaded the sample project agentic rack system. So basically rack systems with some agents. And what you see here is the Git integration. We see that we have the GPU configuration. We have Docker Compose. We have a project container, which is basically a collection of information about packages, scripts, environment variables, mounts, and so forth. And there's also application integration, which is basically like opening Visual Studio with a remote endpoint into your project, where it is, like on the DGX Spark, Jupyter Lab, TensorBoard. TensorBoard is a visualization toolkit for machine learning experimentation. And yeah, I can also open the chat application, which is the project, and can just test it out. Should open. It's probably not running. Okay, there it is. There's my application. So pretty cool. Other than that, terminal with SSH connection, cursor and Visual Studio Code open with remote location from the DGX Spark, and the custom tooling is basically, I use the sample for OpenWebUI, which is just a chat interface which automatically downloads models for me, has chat history, and also I can play with parameters like probability, for example, to change the model behavior. Okay, what else? I think that was it for NVIDIA Sync and AI Workbench. Okay, here we go. So that's the website from NVIDIA for NIM. I told you you just run a Docker container and you get the model of your choice, and you just use the endpoint for your applications or whatever you want to test. So that's pretty cool. If you don't want to deal with any configurations, then launchables. Looks like here. Okay, launchables, blueprints, voice agent, for example, super interesting topic, because it's very crucial that you really look at all the optimizations, because of every millisecond counts, because it makes it more natural if you speak to the machine and it answers directly. And so you need to do a lot of tooling in the background and a lot of translation, so that is not as easy. What else? The GPU cloud. This interface is for the container registry. So for example, I get a container with DeepSeek run. I can get a container with Nemotron Nano Flux. Okay, so that is a cool resource. Okay, then there are launchables. Basically, you just can install a project into the GPU cloud. Let's look at Dynamo. Basically recommends what you need. 2 GPUs, 16 CPUs, almost 300 gigabyte of RAM, and recommended as Crusoe or Scaleway, and then you can just deploy it. I would need some credits, which I don't have. And it explains what it deploys and what you can do with it. Pretty cool. Pretty complex systems, so pretty easy to install and to look at it in this way. So now, favorite part, playbooks. So it helps you with basic things like network access, how to connect multiple 2 or 3 DGX Spark, or how to connect it via switch. It helps you with all kinds of like how to convert text into a knowledge graph, all kinds of machine learning systems, dashboard, tailscale, private BPM, vibe coding in Visual Studio, Flux image generation, Dream Boost, that is fun, fine tuning, all kinds of agent systems, CUDA optimizations, robotics, and what else? OpenClaw, NemoClaw, Hammers, all the good agent frameworks. Inference, speculative decoding, MTP, Llama CPP, CSGLang, TIT, or Tensor runtime, NVIDIA's own inference runtime, where you get, when you really want to get everything out of the Spark, you should run TIT LLM. But if it's more about like trying out models and installing them without complications, because every model has a different architecture, then you better go with VLLM or SGLang. NIM, right? Like was an explanation. Basically, it tells you how long it takes. It's most of the time you're much faster. So here you tell it which kind of model, Llama 3.1, 8 billion parameters instruct for the DGX, and then you just run it, and then you fire a call request to test it. So as easy as that. So DGX Spark release notes, I just show this because it's important which CUDA toolkit you use and what is supported actually. So that is crucial. What was interesting too, Spark stacking. At the beginning there were only 2, but now it seems like it's not really limited anymore. Great. And they also have information for enterprise, like if you want to deploy that securely offline. There are definitely, now here, enterprise manageability. There are definitely possibilities to do that. So that's even a completely different space for this machinist. Okay, so the forum. Oh, I love this. Announcement, official announcement, projects, people having issues. Like I had a power draw issue once, but it was simple to solve. I just spent 2 days analyzing it. But people from NVIDIA look into the forum, they respond and they help if there are really issues. So there's active from both sides. There are a lot of people optimizing things and presenting projects. And one of that is Spark Arena, which is basically a website where people can upload benchmarks, and then you can go to the website and then compare models. Like if I want to see the leaderboard, I want to see token generation 128, context concurrency, I want to see VLLM, single node quantization, optimum would be NVFP4. I want to see current model 3.6, for example. So I see some uploads, and it depends how people configure it, I believe, if I interpret it right. But decode maximum is like almost 180 tokens per second, and then you can go into that, get the information from Hugging Face for the model, and you also see some graphs and the configuration, how they set this up. It's pretty crucial to understand what was installed, which versions, how was it compiled, what was used. Otherwise, you will not get the same result, most likely. So that is pretty helpful to get an idea what performance you can expect without spending hours of installing things. Llama Benchy was one tool to standardize benchmarks. So then there's this project called Spark VLM Docker. It's a Docker container prepared with VLLM, and it comes also with a lot of recipes and some support for array, like multi-node cluster. So, and it's they put a lot of effort into testing out parameters and making sure that the recipes are well maintained. So this project comes very handy when you want to use VLLM, very good runtime for a lot of, with support for a lot of models. And this project has a lot of recipes. So what you do at the end of the day, you get the newest VLLM, you compile the Docker container, and then you just run a recipe solo or with Ray support for multiple cluster. You define override parameters, and yeah, that's it. So then there's Spark Run, which is a tool approach and terminal where it's a little bit simpler. So it comes with a lot of more recipes, and it provides also a little monitor, but basically you have a tool, command line tool, where you just run models like this, or recipes with Spark Run, Quensby Run 7 billion on VLLM. So that's pretty cool, and you can also override parameters. Yeah, and also supports multi-node cluster. Okay, something I found, what I learned was really fascinating, which I was not aware of, how crucial the software stack from NVIDIA is. CUDA is a system based on APIs, libraries, and integrations, which is developed for the last 20 years. And it's so deeply integrated and so crucial to the platform. It's also the install base is so huge. CUDA APIs is basically the platform which enables libraries, the CUDA-X libraries, to use all this. Like CUDA APIs are just like, I don't know, 100. Libraries are hundreds, and integrations are tens of thousands. So when I say integrations, it's basically application libraries like machine learning frameworks, all of that. It's huge. And the CUDA-X libraries are specialized for all kinds of things like quantum computing, deep learning, image and video libraries, robotics, and I think that's NVIDIA's strength. Okay, so the real performance on the DGX Spark, I think that is probably everyone is curious about. If you watch the market, then you know that there are a lot of 35B models out there which are somewhat running okay on a laptop or on a MacBook Pro with good RAM and a unified memory and a good GPU. But the DGX Spark allows you to run models in theory up to 200 billion parameter. But let's take the Nemotron 3 Super, with all kinds of optimizations. That runs pretty well with a very good performance on the DGX Spark. And you have a lot of room for KB cache and all the other things you need. You also need a lot of space for other things, like think about agentic system prompts, or maybe your agent reads a whole repository, so it has a 128K context window, and it needs to feed that system, and the system actually needs to calculate the tokens based on this context. So that is a massive amount of data. So, but 120B fits easily in. You can on the DGX Spark, when you have multiple of them, 4 in the best case, you can run bigger models like GLM 5.2. So you can run those models, it works, and you have a token performance around like 30 tokens per second. Like if you have a agentic scenario with a lot of reasonings, and you want a higher token performance like the Qwen 3.6 35 B, that we have seen 180 tokens per second. It's decent. I mean, Frontier is also, they have like around 30 to 50 tokens per second. Not completely true, because all the reasoning loops in the background, they eat a lot of tokens too, and you don't see them. So when you run a 120B model, you get around like 75 with batching and a lot of optimization. I think that's pretty damn good for like local intelligence. Yeah, and then there are also a lot of NVFP4 optimized quantized models, which you should look out for. Sometimes it's good to take FP8, but be careful. Hugging Face has a lot of models, and a lot of people just quantize, but they don't really understand how to test it. So if you have something coming from the creator of the model or from NVIDIA, it's always better. Okay, let's do an inference benchmark. What I have is a quick comparison of a benchmark with Llama Bench. I also have the Sparky run 120B model on Tensor RT. Okay, for this demo, I have 2 terminals. On the left, we see the MacBook Pro with 24 GB of RAM, and on the right, we see the DGX Spark. For the test, we use Llama Bench from Llama CPP, a good inference runtime to run models locally. It's the only runtime which run on both, so that's why I was thinking this is a good comparison. Of course, for the Mac, I could do the MLX platform, and on the right, I could use Tensor RT, so that would be a huge difference. As model, we have the Qwen 2.5, 7 billion parameter instruct model, quantization GGUF. Same on both sides. And we have 5 tests of the prefill test with 512 tokens, and the token generation test with 256 tokens. Like I said, 5 repetitions each. Let's give it a go. On the Mac, it will take much longer. You will see that on the right, we use CUDA. Prefill is already done. Over 3,100 tokens per second. Prefill test, and then the decoding test takes a little bit longer. On the left side, you see that the backend is actually metal. It's not unblast. It's not bad. It's actually pretty good. But it's still, it is a MacBook, and it only generates or can process prefill tokens only with 190 per second. Huge difference. On the right, we have already the result for the token generation. It's around 45 tokens per second. And on the left, we need to wait a couple of seconds till it's generated. Here we go. It took a minute. It got 14 tokens per second. So that's definitely a huge difference. Okay, let's do a quick Tensor runtime inference demo where we run Tensor RT by NVIDIA in a Docker container and reload the OpenAI GPT OSS 120B model to get an endpoint to test the endpoint, basically. Okay, this will take a while, almost 2 minutes. And now we have the endpoint, and now we can fire a curl request to the DGX Spark from my MacBook Pro using the OpenAI chat completions endpoint and using the model and just asking for some facts about the octopus. So let's give this a shot. First request may take a little bit. Here we go. All right, let's do the same thing again. Now it should be a little bit faster. So you see it's a little bit faster. That was the whole demo. Okay, that was the inference benchmark. The comparison was DGX Spark versus MacBook Pro. I used the Llama CCP inference engine, and we had a prefill with 512 tokens for prompt processing, and we had a token generation with 256 tokens for the generation of the tokens, and 5 tests each, so that we actually get a good feeling for the rich. So then I had another demo running with Tensor RT. The runtime, what we saw was like simple requests. And okay, so that was a takeaway. Now I have a demo where I want to show you what it means to actually use CUDA. What I have generated are 200,000 text lines with complete nonsense. And what I want to do is to process the data to actually generate tokens. Okay, what I want to show you first is the data. So what I generated is a lot of nonsense in different text lengths. So every text block has a different length. We have 200,000 lines. So we want to run it only on the CPU. The test tries to find vectors for the text blocks, and it has a warm-up phase and it has a measurement phase of 16 seconds. So now when we have all 3 results, I'll quickly summarize. So you see that with just running it on the CPU, so no GPU utilization, we only can process 160 text items, line items per minute. And yeah, it's a fixed batch size, so we just take 32 lines. So then next is run GPU naive, which is basically using CUDA, fixed batch size 64, so a little bit bigger, no bucketing, so we don't really make sure that we have like the same text length in one bucket. So we still have some wait time, and there's some, we fully use the GPU. We only need 600 milliseconds, and we can process around 100 per second. So we processed 6,272. Then the last test is where we have everything optimized, where we use token bucketing with 256 batch size, I believe. And all of a sudden we can process, I have seen 900, but we processed 46,000 lines. So for this demo, we used a Chinese embedding model. Basically, the use case is you have a huge base of text and you want to create vectors to actually enrich your LLM requests, or to be able to retrieve the data. We tried to use a token budget, used batching, and we also used bucketing, which means that we had batches with different lengths of text to avoid a wait time. And you saw that's makes a huge difference. Okay, so last slide. What is the superpower of Sparky? I think it's top-notch hardware. I still don't see anything comparable in the market. I'm super excited to see something, but at the moment it's just too expensive and doesn't really bring the performance or the enterprise capabilities the DGX Spark has. Remember, the DGX Spark is not replacing the cloud or making a laptop any faster. It's just a very good device to learn and to prototype and to test. So for me, my experience was less friction, less memory limitations. There's plenty. Fast iterations, no cloud overhead. It's easy access. I'm really, really grateful that NVIDIA put so much effort into providing this device and also the software and all the guidance around it. So I think that can be your local AI lab. And for me, it truly is. So thankful and keep learning.